Any problem from this paper? Which was, could you manage time to attempt anything?
Yes, sir.
আচ্ছা, প্রবলেম নাই।
No, sir.
আচ্ছা, ঠিক আছে। সো এই চ্যাপ্টার আমাদের আপাতত শেষ। আপাতত বলতেছি, I'm saying for the time being, because whenever we'll solve some more question from the past year question papers, because this question compilation is not up to the very recent year, we might come across some new problem and which we will include for our question. Asif, you are asking for number 2 and number 4. Yeah, well, number 4 has already been discussed in our lecture classes, so I'm not going to show this over here. You should look up for in the lecture classes in the YouTube videos when they are uploaded. If they're not uploaded already, they will be uploaded pretty soon. We can talk about number 2. Number 2 says thermal thermometer or condenser voltmeter is used to measure the temperature in a flame in the Bunsen burner. Figure 3.1, draw a label diagram for the structure of thermal thermometer as it. We also discussed number 2 in the last class as well. I asked you to draw the diagram as per your own as you can, and then I discussed how this is actually used, how the thermal thermometer is actually fed data, and calculations are done yesterday. So we actually discussed these two questions. If you didn't do them because it happened yesterday 9:30, I'll upload the video. You should look it up from there. Anyway, irrespective of that, we're going to start the discussion for the next chapter, which happens to be heat capacity. So I'm going to start writing here, and I'd like you to write whenever you need to write. I'll tell you when you need to write. Where is my okay, there it is. So the next chapter that we're starting is called, it can have a lot of different names from your syllabus. I prefer to call it heat capacity. Heat capacity and latent heat. There are multiple different things that we're going to see in this chapter. The first thing we're going to see, learn about temperature time graphs, which is important. And we're going to learn about heat capacity. Specific heat capacity. I think that's pretty much it for this chapter. Evaporation comes on the next chapter, the gas laws, or the what is it called, kinetic theory of matter. Well, I'm going to keep two more bullets free over here. If something else comes up, I'm going to write it up over here. So the first thing that we understand are temperature time graphs. What are temperature time graphs? Well, as the name indicates, this is a graph of an object which is undergoing temperature change, where the temperature is plotted on the y-axis, time is plotted on the x-axis. In most practical cases, the temperature on the y-axis is given in degrees Celsius scale. And for most practical cases, for a heat experiment, the time is usually measured in minute, not in second. We can also measure in second. We can also measure in hour. It doesn't matter. Typically, for a laboratory experiment, we prefer the time unit for minute, because any heat experiment usually takes a pretty long time, whether you are heating it up or cooling it down. It takes close to 10-15 minutes. So plotting the temperature graph in a minute scale actually helps us to avoid large numbers, because if we plot them in seconds, the numbers are going to be pretty large. So scaling can prove to be slightly more difficult than what we are comfortable with. Although it's not impossible, but that's the most common variation. A couple of things that we need to understand, that There are basic three substances that we basic three state of matter that we talk about. What we call is these things are solid, liquid, and gas. Among these three states, we can have conversion among these three states, vice versa. When solid converts into liquid, we call this melting. Sometimes it is also called fusion. Although fusion in terms of in nuclear sciences, fusion can have a different meaning, but sometimes we can also use fusion, melting or fusion. And then when liquid turns into gas, we call this boiling. Liquid can also convert into gas in terms of evaporation, which is also another type of liquid to gas conversion. So evaporation can also be another form. We're going to talk about this in detail in the next chapter. When the gas converts into liquid, we call this condensation. And when liquid converts into solid, we call this process, what is it called? Uh, Freezing, or sometimes it can be also called solidification. So these are the process name for four different type of changes that an object can undergo depending upon its initial state and its final state. What you need to understand that melting and freezing are just the opposite process, whereas boiling and condensation are just the opposite process. So it also just so happens that for a pure substance, this is important word, for a pure substance, an object's melting temperature or freezing temperature, depending upon the type of conversion that you're doing, whether we're doing solid to liquid or liquid to solid, this is a fixed temperature if we take a pure substance, irrespective of the amount of mass. If you take, let's say, 100 gram sugar, and if you, in another example, you take, let's say, 1000 gram sugar, if you start to apply heat to both of them, provided that the sugar is pure, we don't have any impurities added, we both of them will start to melt at the exactly same temperature. And then if you start with some liquid sugar and allow it to cool off in room temperature, both of these two things will start to solidify or freeze at the same temperature as well. So this means that this temperature is a constant that depends upon the choice of material, or we can say only material. This is a constant for a pure substance which is dependent only in its material. This is not dependent upon the initial amount of substance that we choose. This is not dependent upon that. Similarly, whenever we're gonna boil some liquid, we are gonna call this process boiling. If we have some liquid and if we have some gas and we convert it into liquid back, we call this condensation. This is a heat addition process. This is a heat extraction process, or you can say this is a cooling process. So this is heating, this is cooling. And also for a pure substance, the boiling temperature or the condensation temperature, which happens to be the same, but they are just called two different names depending upon the direction of the heat transfer. If we're adding heat, it's the boiling temperature. If we're extracting heat or cooling the object down, it's called the condensation temperature. This temperature is also same for both the processes, for a pure substance, that is. And one more thing you need to understand, actually I'm covering a lot of basis from the kinetic theory of matter, because to discuss these parts we need to actually talk about those things. I discussed about the structure of solid, liquid, and gas in one of our earlier classes. And you should recall that in the solid, the particles are stuck in their fixed position. The only type of motion they can have is vibration, and they cannot move away from their fixed position. All that they can do is they can vibrate a little bit about their mean position or equilibrium position or rest position. All of these three, either of these three things you can write: mean position, equilibrium position, or rest position. And these particles have some significant intermolecular force between them. That's what keeps them in their fixed position. If you start to apply heat, if we start to apply heat to a solid object, these particles are gonna grab that heat, and they're gonna start vibrating really. They're gonna increase their vibration. Increased vibration can mean two aspects. It can either mean increase of the amplitude of vibration, or it could also mean increase of the frequency of the vibration. Well, the solid particles have increased vibration, and eventually their vibration becomes so vigorous that they start to vibrate so vigorously that they can overcome the intermolecular attraction force. That not overcome, sorry, I'm mistaken. They can actually have enough energy that they can now break free from the structure and start to move around on their own. This is what we call the liquid state. In the liquid state, particles are still touching each other, but they are basically not stuck. Pretty much similar to what you can think about for granulated sugar. If you think sugar in a solid state, if you roll sugar, you can see that the sugar actually flows down because it's all converted into small tiny crystals. So that's basically how the liquid state is. Particles are still touching each other, but they are not stuck in a fixed position. They can move around. So to achieve from here to here, and then of course there is a case of gas where the particles are absolutely free from each other. They don't have any intermolecular attraction force between them, and they're really far apart from each other. They have no fixed volume and no fixed shape either. So these are all heat application process. What you need to understand that to convert this object from here to here, it will take some significant amount of heat depending upon how many molecules are we starting, are we trying to detach from their fixed position. If you have few particles, you're gonna provide them less heat. If you have a large number of particles, if you take a huge amount of mass to begin with, start hitting that, then you're gonna definitely take a longer amount of time. But irrespective of small or less, the temperature at which this will happen, that temperature, let's say theta of melting, so this 30 degrees Celsius would be same for the same thing. If you have a large amount of mass, it's simply going to take longer. If you have a small amount of mass, it's simply going to take smaller. And now you might wonder, where is the time factor is coming from? I mean, what to do with the time? The idea of time is very important because energy equals to power into time. So power basically means the rate of heat transfer to the object. Time is the time. The time is basically time. If you multiply these two quantities, you get the total amount of energy supplied to that substance. What I want you to understand that whenever we're trying to compare these two things, hello,
Sir, could you repeat what P stands for in the
P is
equation?
the power of heat transfer. I'm going to write power of, I'm going to write heat exchange because sometimes it can also mean heat extract. So I'm not going to say heat applied. Heat exchange is uh, a more general word. It could mean taking the heat out of the object, cooling, or putting heat into the object, heating. So this is the power of heat exchange, or it can say, think about the unit, joule per second. So how many joules of energy is entering into the object for a heating case or leaving from the object for a cooling case every second. Joule per second basically means that. If we multiply that thing by the amount of time for which the heat was applied for a heating case, let's say I'm going to stick to that, then we can calculate the total amount of energy that was supplied. If we start with a large amount of substance, you're going to need more energy. More energy from the same power supply can only happen after a long amount of time. Now there is a catch that you really need to understand. Consider a scenario. Say you have a pot of water, basic pot, মনে করো ভাত রান্না করার পাতিল. Okay, so you have a pot of water. To make sure that this pot of water is currently at room temperature, so let's say the temperature of this thing is 25 degrees Celsius. If we want to boil this water, we need to apply some heat to the cooking pot, which will eventually go into the liquid water, and ultimately this water will start to boil. So which means we need to provide heat. Now, think carefully. If we light up a candle, normal candle, under this thing, well, obviously this thing is supported by some holder and everything. If we light up a candle under over here, we actually start supplying some heat, and this heat is gonna heat up the metal pot, and also the heat will enter into the water. My question is, using a candle, can we boil this water? What does your regular life experience tell you? Can we or can we not?
না স্যার,
We can, but it will take a lot of time.
It's not that
অনেক টাইম
efficient.
লাগবে।
Okay, I have quite a good amount, quite a good number of nice responses. They are very intuitive. I appreciate it. Uh, what we need to do to make sure that this water will be boiled?
We have to, আমাদের
Use
হচ্ছে
burner?
কি এটার টেম্পারেচার দেখতে হবে বয়েল
Well,
করার জন্য।
well, the temperature of the water is 100 degrees Celsius. The question that I'm asking, that what we should do to make sure that this water boils. So we can place a thermometer over here by keeping the candle over here. Observing the thermometer is basically reading the temperature. Would that ensure this water is boiled? Of observing the temperature, would it make sure that this water will boil?
না
No.
স্যার,
So what is actually missing here? Here's the deal. Whenever we apply heat, or we are thinking that heat is going to enter into this thing and eventually this is going to heat up. So logic tells us that, or basic understanding of heat transfer tells us that we are providing heat from the flame, the heat will enter into the water temperature will rise slowly, and eventually this water should come to 20 to 100 degrees Celsius. because intentionally I gave a candle. The candle doesn't have much to power. It does not actually produce a huge amount of heat. So essentially it's going to take a long amount of time because the heat has to go there and eventually raise the temperature bit by bit, and eventually it should reach 100 degrees Celsius. But to tell the truth, in a realistic scenario, this one candle under a cooking pot worth of water can never start boiling this water, because you have to understand this whole thing is actually in contact with atmosphere. The moment we start heating, here's the deal, listen to me very carefully, the moment we start adding heat to this container, the temperature of this whole thing, consider the container and the water, they all have the same temperature at any point for the sake of simplicity. The moment we start applying heat, the container is going to start heating up, and the moment the temperature of the container and all the water inside temperature is higher than the atmosphere, this will become the hot object and the atmosphere will become the cold object, and they'll be in contact with each other. Whenever we place objects with two different objects close to each other, it will always happen so that the hot object will lose heat to the cold object. Hot object will always give up heat, and cold object will always absorb heat. The problem with the and the rate of heat transfer is actually dependent on the temperature difference. This is something that I showed you in one of our earlier classes. I showed you that if we have a temperature versus time graph, and we start with a hot object and eventually start to cool it down, this cooling curve actually becomes like this. It becomes asymptotic with the room temperature, because when the temperature difference is large, more heat will be lost per second. When the temperature difference is low, less heat will be lost per second, and this keeps on happening. In the same way, whenever we are starting to heat this object, this was for a cooling curve. So initial temperature was high, we are slowly losing heat. And if we try to consider for a heating curve, let's say this is the room temperature level. We are starting the water pot and the water to start heating up from this point. Initially, let's say after some time, this much time, I'm gonna copy this amount of time. Actually, let me just copy this equal distance anyway, about 1.5 divisions, for example. So within this amount of time, the temperature of the water, let's say, rises to here. So we have this much temperature increase over this much duration. In the next equal amount of time, the temperature rise will not be as much, because you have to understand that when the water was kept at this temperature, 25 degrees Celsius, this is 25 degrees Celsius. When the water is at this level, we don't have any heat loss. The moment the temperature of the water starts to rise, it starts to losing heat. So this is going to happen. What happens for the next half cycle? You have to understand that at this point, for this duration, for this second equal duration, the initial temperature of the water is already warmer than the atmosphere, and then eventually it should reach a even higher temperature, which means the average temperature for this much duration is lower compared to the average temperature over here, which means more temperature difference will cause for the heat to loss to the surrounding more rapidly. The higher the temperature difference between the cold and the hot object, the more rapidly or the energy transfer will happen. More rapidly in this case basically means higher power. Rate of energy transfer will become higher. So the amount of joule per second transferred from the container and the water out in the atmosphere will become higher. So because the heat lost it will become higher, essentially we can say the heat gained amount or the temperature increase amount should become smaller than before. So let's say in this case, for the first duration of this segment, we had a temperature rise of about 1.5 division of this graph. It is very much possible for the next duration of next equal duration, the temperature rise is not going to be as much, because over here for this much duration, the rate of heat loss is significantly larger compared to the rate of heat loss over here. Here, that object was more close to the atmospheric temperature, so the heat loss was quite small. But here, the object is at a significantly higher temperature than atmosphere, so heat loss will increase. And this will keep on happening, keep on happening, keep on happening. If we apply a candle over here, pretty soon, this curve of temperature increase will become horizontal. And by horizontal, I mean perfectly horizontal, not asymptotic. It will become perfectly horizontal. Whenever the curve is becoming horizontal, this temperature time graph becomes horizontal. It means this is such a scenario where the rate of heat input and the rate of heat output are equal. And this is what we call a state of thermal equilibrium, that the object is not undergoing any temperature change. So if we slowly try to measure the heat amount of heat loss, or somehow we can measure the rate of heat output from a candle, we can say that for this amount of part of the time, the rate of heat supplied by the candle is exactly equal to the rate of heat loss to the surrounding. So whenever these two things will happen, the temperature will come to a steady value. Now, using a candle, because it doesn't have too much of a strong heat source, it's a pretty timid heat source, this constant temperature value, this level will never be 100 degrees Celsius. It will be at a certain liquid case. You can try this experiment at home. You shouldn't have to go far away, but you will find out that the temperature of this thing might as well be, let's say, what 50 degrees Celsius, maybe, but the temperature will not rise anymore. এই পার্টটা কি বুঝতেছো কিনা যে এটা যে পসিবল, এটা কি বুঝা যাচ্ছে? Anyone?
স্যার একটু বলবেন না, বুঝতে পারিনি।
When the temperature will start to increase, what the first thing that I said, that the increase of the temperature will happen in a decreasing gradient, which means you're gonna have less increment for every equal amount of duration as the temperature of the object goes up, because more heat loss will happen compared to earlier. So gained heat or stored heat will become small, so that temperature will increase will also be small compared to earlier. So here we had this much temperature increase, here we have this much temperature increase, here we had only this much temperature increase. So the farther you go to the right, the increase of temperature will become smaller. That's what I say. And
ওকে,
when the object reaches equilibrium means the temperature is not increasing any further. It means this is the point where the power in equals to power out. Here the power in is happening from the flame, power out is happening due to the atmosphere. So whenever these two things will become equal, the object cannot heat up any further temperature. It will hold that temperature true. And this is a state that we call thermal equilibrium. Thermal equilibrium.
তো স্যার আমার একটা কোশ্চেন আছে।
বলো।
স্যার যদি ওইটার উপর ঢাকনা লাগাই দিই তাহলে?
যদি ঢাকনা লাগাই দিই এবং ক্যান্ডেল ইউজ করি, তাহলেও আমাদের ইকুইলিব্রিয়াম টেম্পারেচার হইতে পারে, বাট সেটা হয়তো একটু বেশি হবে। অবশ্যই ঢাকনা লাগাতে আমাদের ইকুইলিব্রিয়াম টেম্পারেচারটা আর একটু বেশি হবে, বাট equilibrium temperature power possible, because I'm by stating that we are using a candle as a heat source, I'm assuming this candle is not like one of those large big candles, a regular candle like 5 টাকা দামের candle. বুঝছো?
জি স্যার।
আচ্ছা, আপাতত এটুক থাক, আমরা নামাজের জন্য কিছু ব্রেক নিব। উইল স্টার্ট ট্রাই টু রিজিউম দ্য ক্লাস at around 6:08, 6:10 or 6:12. Thank you very much. I mean, break. Class is not over. Yeah. Resume the recording. So because the temperature is pretty low, because the heat supply sources has a pretty low power, so it's impossible that the temperature can reach up to 100 degrees Celsius. So the flat lines on temperature time graph does not essentially represent state change. However, if we replace this candle with a strong flame source, for example, let's say if we place a Bunsen burner over here, or we put it onto the stove of our kitchen, and we give it a very fierce heat source, it is possible this temperature from the room temperature can rise all the way up to the 100 degrees Celsius. Let's say this is the temperature graph where this is 100 degrees Celsius, and that's where the temperature will get stuck for a certain duration, because that's when the water will start to boil. So I should show this reference line as dotted lines. So this is where this is 100 degrees Celsius, and that's where the curve is gonna take a bit of a curve over here. Why the curve happens, I'll explain this. And then the temperature starts to become constant for a significant duration. So what happens within this part that the temperature is remaining constant? Within this part, the water molecules are converting from liquid state into gaseous state. Whenever liquid converts into gas, the particles are absolutely made free from each other's attraction. You have to understand that here the particles have significant attraction between them, which is much lower than the particles of the solid, but they still have measurable significant amount of attraction force between the intermolecular attraction force is still pretty strong. Not as strong as solids, but it's quite strong. That's why the particles are held together and we have the state of liquid. But whenever we have a gaseous state, the particles are absolutely free from each other. So you have to try to think about that. Particles are here stuck by some intermolecular forces. If we want to separate them out, we have to actually detach them from the attraction of all the other neighboring molecules. So they are stuck with each other, and to convert them into liquid, we have to separate them out from overcoming the intermolecular attraction force. Here I'm using the term overcome. Overcoming means to altogether break free of each other, altogether get away from each other. So we have to overcome the intermolecular attraction force, and that's how we can achieve the state of gas or steam. For water, we call the gaseous state steam. This would require a significant amount of energy, and as long as that process keeps on happening, the temperature of this water will remain stuck at 100 degrees Celsius. It will not increase, because at 1 atmospheric pressure, water cannot become gas or water cannot convert into steam above 100 degrees Celsius. The boiling temperature for water under 1 atmospheric pressure is exactly 100 degrees Celsius. So that's why the temperature will stuck for a significant duration of time. Let's say if we could capture all of these steam, let's say we are performing this experiment in a closed large container. There's a huge container over here, and we are trying to capture all the steam. As long as the water will produce steam, and eventually the, let's say the container gets altogether empty and all the steam is now contained within this part, and if we still keep on heating this, allowing this heat to go by, then the temperature of this entire room where the steam was kept, I'm drawing a very large room because now the gas molecules or steam molecules have to have significant large gap between them, so there's a huge amount of volume expansion, like a huge proportion of volume expansion. So once the temperature, once all the water has been converted into steam or the boiling process is finished, then we, and if we keep adding heat from that point onwards, then it is possible that the temperature of that steam amount will actually start to rise once again. The point that I'm trying to show you over here, so the ultimate graph is actually taking a shape like this. So we have a linear increase. I actually for mistakenly drew a bit of a curve. This should be linear. We're actually increasing the temperature significantly, straight line, nearly straight line, and then we are converting the state change, and then once state change is over, we're having the temperature increase once again. So this is the part where the whole substance is liquid, only liquid. This is the part where liquid is converting into gas, so liquid plus gas, or you can say liquid into gas. That also works. So this represents a mixture of liquid plus gas within this large container, and this in this part, this is entirely gas. If we keep adding more heat, this it will still go on for higher and higher temperature, and eventually this gas can have another fourth state of matter, fourth state, which is not a part of the syllabus, which we call plasma. Not very easy to achieve in earthly environment, but it is the state of substance where the energy of individual atoms is so high, it is so damn high, that the entire structure of atom actually collapses. A plasma state is basically a hodgepodge of nuclei and free electrons. So it's just a
Sir, what is hodgepodge?
hodgepodge মানে খিচুড়ি. It's just a
বুঝছি
mixture.
স্যার।
It's just a unorganized mixture of nuclei and freely moving nuclei and what and electrons. So the structure of atom is no longer existing when in the state of plasma. You don't have to know these stuffs. I'm telling you that because I want you to know that there is a fourth state of matter, which is plasma. It is usually naturally available at the core of most of the star, where the temperature is extremely high. For the fusion process to occur, we need this state of plasma. However, for your heat syllabus, this is not included, so you can altogether erase this from your memory if you want. You don't have to consider this. But for our syllabus, we only have to learn about solid, liquid, and gas. So lastly, to summarize the whole discussion, number one, horizontal line in the temperature time graph does not essentially represent state change. It could represent thermal equilibrium. When it would resuming the class, one of you was asking a question about this thing. Anyone? No. Okay. So this is the important part that we have got from this information, that we have to supply heat, and then as long as the temperature increases, that means a single state. When the temperature becomes constant, if the temperature where that constant temperature or the horizontal segment of the graph happens is the transition temperature, I mean, it's the word transition because this is the state change temperature, then this would mean state change where we have liquid plus gas. It's a mixture of liquid and gas. And once all the liquid is boiled to gas, only then the temperature will start to rise up to this point. So that's the basic idea for this discussion. Now, how can we, for this chapter, we're going to actually see that how can we calculate the relevant amount of heat required for these processes to achieve for a certain duration of time, and so on and so forth. So here comes the discussion of these points. The first definition that we're going to see is what we define as heat capacity. I'm going to tell you the definition. You don't have to write them. Just hear me out. Heat capacity of an object. I'm using the term object. Remember this thing. Heat capacity of an object is given by capital C equals to E over delta theta. The unit of this thing is joule per degree Celsius or joule per Kelvin. The way we define heat capacity is like this, that the amount of energy required to change unit temperature of the object is the heat capacity of that object. I'll say it again. The amount of energy required to make unit temperature change of an object is the heat capacity of that object. Or you can start from the left side. The heat capacity of an object is the amount of heat required per degree Celsius temperature change, or per temperature change, or for unit temperature change. Per unit, it must mean the same thing. Per unit temperature change, you can also write that as well. So that's the definition for the heat capacity. Specific heat capacity, you have to understand this term, that whenever we use the term specific for almost all of the physics variables, where physics quantities, where we use the term specific, it means something divided by mass. For example, in physics, the word rate always means something divided by time. Rate of work done is power. Rate of energy transfer is power. Then rate of charge flow is current. So something, a rate of velocity change is acceleration. So whenever we use the term physically rate, it basically means some quantity will be divided by time. In the same manner, the word specific in physics almost always means there will be some quantity that should be divided by some amount of mass, or what happens per mass, or what happens for 1 kg of mass, unit mass. Specific capacity is given by, the symbol for specific capacity is small c. They both have the same shape. Capital C and small c doesn't have much of a difference. I'm just showing, writing them one as large and one as small. You should also try to do that. Specific capacity is given by E divided by m delta theta. The unit is given by, have a look, the energy of unit of energy is joule, mass is kg, and delta is degree Celsius or degree or Kelvin. So the unit of specific capacity is given by joule per kg per degree Celsius, or joule per kg per Kelvin. One thing that you should keep a very good eye on over here is that while writing the symbol for kg, that k is a small k, because it is the symbol for kilo. Kilo comes is with a small k, and the Kelvin comes with a capital K. We remember this capitalization factor. Do not mess this up. Kilogram K is small letter, and Kelvin K is capital letter. So be careful about that. So the way we define the specific capacity of the material of an object, that's the difference. Specific capacity happens to be a property of the material of the object. This is something similar to density. But if you learn in your density chapter that density of an object is not the property of the object itself. If multiple objects are made with the same material, no matter how big or how small, irrespective of shape or size or volume, their density will always be the same, provided that they are all made from the same material. So density is not the property of a definite object, it is rather the property of the material of the object. So specific capacity is a similar thing. The way we define is that specific capacity of the material of an object, specific capacity of the material of an object is the amount of heat required for unit mass of that object to change the temperature by 1 degree Celsius or 1 Kelvin, or to make unit temperature change. You can say all of these stuffs. Amount of heat required per mass per degree Celsius. That's the important bit. If you can remember this unit, that also helps. So that's the key difference. This is a property of the object. This is not a property of the object. This is a property of the material. So let me just show you a bit of a mathematical conversion using this equation. I'm going to write them over here. If I cross multiply this equation, I can write E equals to capital C to delta theta. If I cross multiply this equation, I can write E equals to m small c delta theta. So you can see that amount of heat required, amount of heat required can be, or amount of energy required to change delta theta temperature change. We can express that information. We can multiply that by heat capacity, and that will be the energy required for the process. And for specific capacity, this would be mc delta theta. So this is the thing. If you just compare these two equations, or you can divide this equation and eventually go for that, delta theta delta E crosses out, you can pretty much write that heat capacity of an object is equal to mass of that object multiplied by specific capacity of the material of the object. C equals to mc. So basically this means that if multiple objects are made with same material but they have different mass, some are big and some are small, if they're all made from the same material, all of their specific capacity, small c, would be exactly same. However, the one that has a bigger mass will always have a bigger heat capacity. It means to make 1 degree Celsius temperature change, to make 1 degree Celsius temperature change of that bigger object would always require bigger amount of energy, which is very obvious for you to understand. You do understand that. Let's have a look. If we are trying to heat up some water in a tea kettle, a very small tea kettle, or a teapot on a chai pati, which is very small. So if we keep some water over here, and if we take a cooking pot for a very large cooking pot, and if we also take water over here, for the boiling process to happen, both of the water's temperature must rise to 100 degrees Celsius. Now, for those who have some experience with cooking stove or about the kitchen, if you have ever tried to boil some water ever in your life, সামি আমার কথা শুনতে পারতেছো না?
স্যার এখন শোনা যাচ্ছে স্যার, আমি রিজয়েন করছি।
ও আচ্ছা আচ্ছা, ওকে ওকে ওকে, থ্যাংক ইউ। এক মিনিট। এই যে হুলি হুলি হুলি, বসো বসো বাবা, বসো। So if we put both of these two cooking pots, those are filled up with water, I intentionally drew half the water in the teapot and more water in the large pot, and if we put them on the stove having the same flame, let's say maximum flame, you do know, or you should know, that the left one will start boiling earlier and the right one will start boiling much too later. It will take significant time for that one to start boiling. Start boiling means the temperature has risen to 100 degrees Celsius. As long as the water does not start to boil, it means the temperature is still below 100 degrees Celsius. And because we are applying heat to this object, it means that the temperature is rising and rising and rising, but not up to 100 degrees Celsius yet. So this is basically a comparison for the heat capacity. Heat capacity basically means how much heat is required to make 1 degree Celsius temperature change of the whole object. Whereas specific heat capacity means how much energy is required to make 1 degree Celsius increase of 1 kg of that object. এই ডিসকাশনটা বুঝা যাচ্ছে কিনা? Any questions so far or confusion so far?
Sir,
Yes.
so is there a specific equation that links heat capacity and specific heat capacity?
Yes, I just
Specific
squared
equation
that.
for-
That squared equation that you can see, there's a diagonal rectangle over here. That is the equation that relates these two quantities. Heat capacity of an object equals to mass of the object multiplied by specific capacity of the material of the object.
This is the one.
This is the one. Yes, precisely.
Okay, thank you, sir.
Sure. It simply means that if if the material of an object has a specific capacity of, let's say, 10, if you have 1 kg of that object heat capacity would be 10 into 1 into 10. If you have 2 kg of that object, it will be 20. If you have 100 kg of that object, it will be 1000, like that. Specific capacity is material dependent property. As long as you choose same material to make multiple different objects, all of them will have the same specific heat capacity. Whereas heat capacity is a mass and specific capacity dependent variable. So if you have a bigger mass, it is supposed to have bigger heat capacity. If you have a smaller mass, it will definitely have much smaller heat capacity. That's the idea. বুঝা যাচ্ছে? Any further question about this part? Anyone?
No, sir.
আচ্ছা, এরপর আমরা যে জিনিসটা দেখবো সেটা হচ্ছে লেটেন্ট হিট। what do we understand from this? Okay, here from this part, we actually need, these are the three equations we're gonna need later to do some mathematical conversions. So I'm gonna you put some rectangle. Oh my god, I'm gonna put some diagonal what tilted rectangle around them. So we're gonna need these three equations in applicable cases to do some calculation. So let's keep it that over here. Then comes the term latent heat, and you can see over here I have used the term specific in bracket. Why not write two different definitions, latent heat and also specific latent heat, differently? Why didn't I do that? Because in most cases, whenever we say the latent heat of an object, in many cases it can actually mean specific latent heat. I mean, in your question you can, in some cases in your question you can also have as given data that latent heat of melting of ice equals to something joule per kg. So you can see over here that this is actually joule per kg. Joule per kg means this is a joule amount divided by the mass. So this is not supposed to be latent heat. This is supposed to be what? Specific latent heat. But in many cases, this word is not mentioned because it is considered that students will understand that this is specific latent heat from by observing the unit. So এই জিনিসটা একটু খেয়াল রাখতে হবে. Let me explain what is the meaning of this. The word latent means hidden. The reason we call it hidden heat, because have a look at the temperature time graph that we have discussed a bit earlier. When the object undergoes state change, in this case liquid was converted into gas or water was converting into steam. When the object undergoes state change, then you can see that we are applying heat. The object is absorbing heat energy, but there is no observable change of the temperature. The water and steam, they are both maintaining the same temperature of 100 degrees Celsius. So we are applying heat. The heat is not making any temperature change. So apparently the heat is getting hidden somewhere. That was the idea of the scientist who was doing the experiment. And then that's why they defined this term as latent heat, because the heat is getting hidden within the object. The object is eating up deep. The object is absorbing that heat, but the temperature of the object is not changing. It is not increasing. Hence the term latent heat is coming from. Now, the way we define latent heat, if we want to specify, or if you want to differentiate this between the words latent heat and specific latent heat, it's very simple. Latent heat means heat. Any amount of heat is basically energy, so that will have a unit of joule, whereas specific latent heat would have an energy of joule per kg. So I can write that latent heat of an object can be given by the amount of energy required per mass. The unit can be given as joule per kg. Sometimes you can also have joule per gram in your question. If it shows up in gram, then we have to know the necessary conversion for how to convert into kg, or it can work vice versa. But it will always be some amount of energy per mass. So that's the basic equation for the latent heat, specific latent heat, energy per mass. The way we define this thing is that specific latent heat of the material of an object is the amount of energy required to convert 1 kg substance from one state to other. So if you're saying that latent heat of fusion, then we can say that the object would be converted from solid to liquid. If we say it is latent heat of vaporization, then we have to consider that the object is converted from liquid into gas. For both of the cases, the unit will be joule per kg. এই পার্টটা বুঝা গেছে কিনা? We don't have per degree Celsius over here because you have to understand the term latent heat. This is exclusively applicable for state change. This is exclusively applicable for state change. And when does state change happen? When does state change happen? State change only happens at a constant temperature. Melting happens at melting temperature. Boiling happens at boiling temperature. So because state change always happens at a constant temperature, that's why latent heat, the idea of latent heat, is not applicable for cases where temperature is undergoing change. It is only applicable for cases where temperature is a constant at the melting temperature or the boiling temperature or such. I'm using or such because these things could also mean for backwards. So the value for latent heat of vaporization of ice is the same as latent heat of condensation of ice, which is equals to something. But these two things are exactly same. Whenever the vaporization will happen, this would be, sorry, ice now. Actually, I should write water. Uh, what have I done? Ice cannot be vaporized, so this would be not correct to say this thing. So what I was meaning is that latent heat of vaporization of water is the same as latent heat of condensation for steam. They would have the same value. This would be heating process, this would be cooling process, but they would have the same exact number, and the unit will be obviously joule per kg, energy per mass. বুঝতে পারছি? Any question? Anyone? No, apparently. All right. If we just multiply these two equations over here, we can also get another equation for energy calculation. We can get E equals to M into LF, and we can also get from here E equals to M into LV. These are the two equations that we might also require for relevant cases when we start doing the math, which is going to be the next part of this whole discussion. So we actually got a couple of equations for calculating the energy required for a certain heat exchange process. So if we try to apply this equation for a certain mathematical problem, let me write a question for you over here. And I'm going to show you the solution for this question on my own. And then I'm going to ask you to do something else on your own by yourself. The problem that I'm going to show you at this point is going to be pretty elaborate. It's going to be quite a large problem. In your actual exam, you'll never have to answer such a big problem. I'm going to do this in multiple steps. You will always be asked to calculate for a small fraction of the problem that I'm about to see. This problem that I'm about to show you practically covers all the possible variations of this chapter maths in a single problem. So this math is going to be long, but don't be disheartened or don't be scared of this calculation. This is just long because I wanted it to be long. The actual case, you'll get much smaller fraction of this problem. So let's say this is the question. Minus 5 degrees Celsius ice of 200 gram is converted into 120 degrees Celsius steam. How much heat energy is required? For you to be able to solve this problem, you need a lot of given data. So I'm writing all of this data. C of ice equals to 2100 joule per kg per degree Celsius. C of water equals to 4200 joule per kg per degree Celsius, and then C of steam equals to 1200 joule per kg per degree Celsius. These are all the specific capacity of those three individual states: ice, water, and steam. And then we're going to need the latent heat function. Let's say latent heat of fusion of ice is given by 3.36 into 10 to the power 5 joule per kg. And latent heat of vaporization of water is equals to 2.27 into 10 to the power 6 joule per kg. Why there is such a huge order of magnitude difference between these two values, I'm going to explain this after a while. But a past information তোমাকে দেওয়া আছে. Now I'm going to show you how to calculate this. Now this is the part that you really need to understand. We're converting 200 gram of, let me use another color. We're converting 200 gram of material from one temperature and one state into a final temperature in a different state. So we need to consider the entire steps or entire stages of this whole conversion. Let's have a look. First, we have minus 5 degrees Celsius ice. We know the mass is already given, so mass is not bothering us. If we start applying heat to this ice, what will happen to this ice? Is it going to start melting immediately? Kids, what do you think? If you start applying some heat to a -5 degrees Celsius ice, what should happen to this ice? I'm giving you two options. Will it start to melt? Will it start to heat up? Heat up means it will start to temperature rise.
So it will start to heat up.
It will start to heat up. It will show temperature rise because -5 is not the melting point of ice. What is the melting point of ice?
0 degrees Celsius.
0 degrees Celsius. Beautiful. So by applying heat from -5 degrees Celsius, this will rise up to 0 degrees Celsius. So I'm showing the rise by a vertical arrow. So this will reach up to 0 degrees Celsius. Once it reaches to 0 degrees Celsius, it's going to start to melt. And in that melting process, it will not change temperature. So I'm going to show that process by a horizontal line, because in this process, that temperature will remain 0 degrees Celsius. So I'm going to write over here 0 degrees Celsius ice. And then as it conversion happens, let's say this is where the conversion happens. And then this is going to be 0 degrees Celsius water, right? এটা বুঝছো কেন আমি ভার্টিক্যাল এবং হরিজন্টাল দেখাচ্ছি? ভার্টিক্যাল পার্টটাতে আমাদের একটা ডেল্টা থিটা আছে, বাট হরিজন্টাল পার্টটাতে হচ্ছে স্টেট চেঞ্জ, এখানে কোনো ডেল্টা থিটা নাই। It is the same temperature, so that delta theta is not valid here or not applicable here. If we start increase the temperature of the water's temperature will rise up and it can reach up a maximum of 100 degrees Celsius because that's the boiling point of water. So we are reaching over here at the same state. Have a look. Water is converting into water, only the temperature is changing. So we have a delta theta over here. And then this then this water 100 degrees Celsius water will start to boil, and it's going to take some significant while, more duration compared to how much it took for the melting. Just to give you a visual idea, I'm showing it to it a much longer line. Assume that the horizontal axis is 10 time, but you don't have to, but it's going to work like that, and eventually it will reach to 100 degrees Celsius steam. That's where the conversion finishes. And then the steam is going to start rising its temperature, and eventually, according to the question, the final temperature is 120 degree. So let's say this is the place where the steam is converting into 120 degrees Celsius. So here we have another delta theta. এই ফিগারটা কি বোঝা যাচ্ছে আমি এখানে কি করতেছি? This is not an actual figure that you will ever need to draw. Yes, I do have my baby around. This is not a figure that you will ever have to draw. This is a figure that you need to visualize in your head for being to enable yourself to solve these problems more efficiently.
Sir,
Yes,
does the horizontal line represent the duration?
sort of. The length of the horizontal can represent the duration. The boiling process of a certain substance will always take longer for the same mass compared to the melting process. Why? I'll tell you a bit later. এখন বলতেছি না। All right.
Sir,
G.
sir, is there anything such as the boiling point? The boiling process will require less heat compared to the melting process?
No. Boiling process will always require more heat than the melting process. I'll tell this in a bit after a while. But apart from that confusion about the duration or the more or less heat, does this figure make sense that temperature rise are shown by vertical arrows and state changes are represented by horizontal arrows? এটুকু বুঝা গেছে কিনা?
Yes, sir.
আচ্ছা। So next part, if you're trying to calculate the relevant amount of heat required for each of these processes, we have to understand that for the temperature change parts, we have to use the formula mc delta theta for here. For the state change parts, we have to use m into L. This was melting, so I'm going to use m into L of F because this is the latent heat of fusion. Fusion is another word for melting. And then for this thing, we're going to use, for this process, we're going to use mc delta theta. Once again, for this process, we're going to use m into LV. V in this case is the vaporization. And then once again, for this process, we're going to use mc delta theta. What is really important, I have not written individual suffixes to so that I don't confuse you, but you do understand this mc delta theta is applicable for ice. This mc delta theta is applicable for water. This MC delta theta is applicable for steam. এটা কি সবাই বুঝতেছো? Because
Yes, sir.
you should see over here that we have 3 individual values given for 3 different states of that same material, that is H2O. And it is important that we understand the significance of these three different values. All right. My kid was adamant to grab my microphone wire, which I had to remove from her hand, and she got irritated. Now I gave her a charger cable wire, and she seemed to be. Anyway, so these are the formula that we have to apply. So I'm going to keep this figure in your sight, and also the constants that I've written on top, the information over on top, and I'm going to start to calculate these heat energies step by step. So keep watching. The mass is exactly the same. You can see that the amount of mass that I have used over here is the same over here. MC delta theta MLF, MC delta theta MLF, MC delta theta. So which means I can very well take the total amount of energy for M common. So before I actually show you that, let me write the full detailed form of this energy expression. First, MC delta theta for ice plus MLF for melting plus MC delta theta for water plus MLV for boiling plus MC delta theta for what? This is for what? Steam. So I'm going to take the M common, or if you don't want to take the M common, you can also multiply the M at every single place. This is going to come 0.2, because the question that I gave you, you should see that I talked about 200 gram of material, 200 gram of H2O. So that converted into kg gives you 0.2. So this will be 0. I'm taking the 0.2 out. This first one was for ice. So this is 2100 multiplied by 5 plus 3.4. Sorry, actually I wrote 3.36. So let's use that 3 as a value, because we have 3.36 into 10 to the power 5 plus this one C delta theta. So 4200 into 100 plus 2.27 into 10 to the power 5 plus 1200 into 20. এই লাইনটা সবাই একটু খেয়াল করে দেখো. See if it makes sense to you. Everyone, have a look at this line. This is a long line, but it is only 2 equations, MC delta theta and ML. দেখো, কার কোনো কোশ্চেন থাকলে এই লাইনের উপর জিজ্ঞেস করো.
স্যার
Yes.
স্যার এখানে যে 2100 এর পাশে ব্র্যাকেটে 5 লিখেছেন, ইজ ইট 0 মাইনাস 5?
Yes. Final minus initial.
ওকে স্যার।
দেখো এই পার্টটা সবার বুঝা যাচ্ছে কিনা? This expression, is it clear to all of us? Okay.
Yes sir.
Someone or multiple, all of you do this calculation and give me this number. So that's the three-step expression for the total amount of energy required for this whole process to happen. Now, in your actual exam, you will never be asked. I mean, I have not seen a single problem where you are asked to calculate the total amount of energy required for such a long conversion. What usually happens that sometimes they ask for a situation like this, or maybe a fraction of that. For example, let's say they might ask you that we start from some temperature of ice, then we reach up to some temperature of water.
Sir, is the significant figure needed? Yes, sir. Yes, sir. Yes, sir.
Hello, anyone? আমার কথা শোনা যাচ্ছে?
Yes, sir.
Let's try to give you a scenario for this math and we can understand. You can see that here we are mixing two different temperature of object. One is a 75 degrees Celsius hot object and a 60 degrees Celsius that is cold object. Whenever two objects are combined together or they're kept in thermal contact or they are allowed to exchange heat from each other, heat exchange will always happen such that hot object will, oh my god, that hot object will lose heat and cold object will gain heat, which means the temperature of 3 degrees Celsius water will rise and the temperature of 75 degrees Celsius water will drop. So let me just show these two things over here. Once again, you don't ever have to draw this figure. I'm just showing this to you to make sense or to give you a bit of a visualization for how to think these problems in your head. So this is gonna start grabbing heat from this one, so this is gonna start rising temperature, this is gonna start losing temperature, and this exchange of heat will keep on happening until both of the temperature becomes exactly same. Let's say that temperature is theta degrees Celsius, which we don't know. We are asked to find that out. What is the final temperature of the mixture? Final temperature means that it is the equilibrium temperature of the mixture. So this one is undergoing a drop, this one is undergoing a rise. So the delta theta for this process would be 75 minus theta, big minus small, and the delta theta for this one should be what? Theta minus 3. এই দুটো ডেল্টা থিটার আইডিয়া বুঝছো বলবান? এই কোশ্চেনটা দেখো সবাই, বুঝা যাচ্ছে কিনা? This is the amount of heat the water absorbed, cold water absorbed. This is the amount of heat that came out from the hot object. এই কোশ্চেন বুঝি সবাই?
Yes, sir.
কারণ এটারে somehow ম্যানেজ করে সলভ করে থিটা ভ্যালুটা বাই করো। Take your steps, do it your own. Give me the value of theta. I would like multiple people to share their numbers so that you can cross check it. I'll keep an eye on the chat window. Anyone? কত আসছে? 4200 কেটে দাও, কেটে দিলে তোমার অঙ্ক সহজ হয়ে যাবে। তারপর হচ্ছে 0.350 আর 700 কে 2 দিয়ে মাল্টিপ্লাই করে কেটে দাও, তাহলে আরো সহজ হয়ে যাবে। মানে বলতেছি যে এটা বাদ, সরি কি বললাম, এটা বাদ, আর হচ্ছে এটা দিয়ে রেখে কাটলে আসবে হচ্ছে 2। এন্ড কোশ্চেন করা অনেক ইজি হবে। থিটা মাইনাস 3 ইকুয়ালস টু কত? 150 মাইনাস 2 থিটা, তার মানে হচ্ছে 3 theta equals to 147. So theta equals to, sorry, 153. Sorry. 51 degrees Celsius. This is supposed to be the correct answer. তোমরা যারা এই কাটাকাটিটা করো নাই, পুরোটাকে ডাইরেক্ট গুণ করে দিছো, তাদের প্রচুর সময় লাগতেছে। ঠিক বলছি কিনা? হ্যালো,
Yes, sir.
সো কারারিটা যদি করা যায়, সুযোগ থেকে তাহলে অবশ্যই কারারি করে নিতে হবে। অ্যাটলিস্ট আর কিছু না হোক, তুমি তো 0 গুলো কেটে দিতে পারতা। 0 গুলো কেটে দিলে তো তোমার ক্যালকুলেটরে টিপতে সময় কম লাগে। ঠিক আছে, এই জিনিসগুলো খেয়াল রাখতে হবে যাতে করে আমরা টাইম সেভ করতে পারি। সো এই ম্যাথের ওয়ার্কিংটা বুঝা গেছে কিনা? এটা আরো কমপ্লিকেটেড করা পসিবল, কমপ্লিকেটেড ভার্সন সেটা নেক্সট ক্লাসে দেখাবো, বাট বুঝা গেছে কিনা মোরলেস?
জি স্যার, বুঝেছি।
জি স্যার, বুঝে গেছি।
ঠিক আছে, এখন 7:30 বাজে, আজকের মতো আমি এখানে ক্লোজ করতেছি। তোমাদেরকে আমি এই চ্যাপ্টারের P1 আর হচ্ছে ওই যে আরেকটা যেন কি P1 আর P2 এবং মার্ক স্কিম, তিনটা ডকুমেন্ট তোমাদেরকে আমি PDF শেয়ার করে দিতেছি একটু পরে। তোমরা এখান থেকে আগে P1টা অ্যাটেন্ড করবা, দ্যাটস মাই রিকোয়েস্ট। আগে P1টা অ্যাটেন্ড করবা, আর P1টা যদি শেষ করে ফেলতে পারো তাহলে P2টা অ্যাটেন্ড করো। So we're gonna start solving from the P1 worksheet from the next class, inshallah. ঠিক আছে?
Yes, sir.
ওকে স্যার।
থ্যাংক ইউ। আসসালামু আলাইকুম, আল্লাহ হাফিজ।
আসসালামু আলাইকুম স্যার।
আসসালামু আলাইকুম স্যার।
ওয়ালাইকুম আসসালাম।